See if this sounds familiar. I'll tell you where it comes from. That thing. This is called point slope form. Let me make this a little bit bigger. So this is point slope form. And the reason it's called point slope form is because there is a place for you to put your slope. Like this. That's where your slope goes. And there's a place for your point to go too. So we get a little orange, yellow, ooh, green, lighter green. Your point can go right here. So if you have an XY coordinate point, it can go there. There's a place to plug those in and get your equation. So that's why it's called point slope. There's something else that's kind of cool I'll show you, and it'll be an aside. First, I want to plug those things in so you know what I'm talking about. For slope, I know the slope is 2. I've just generated that. But the two things I need to input are my y1 and x1, which are the coordinates of one of my points. I'm just going to pick an easy set, like the 5, 10 that I have over here. It can be either of the 2 points that we chose for finding our slope. So I'm going to choose this one because it's easier, I think, numerically, and that's as scientific as my method was. And I got to remember y goes here, and x goes there. It was a big pain for me. Sorry. Got it. I saw it that time. And that's effectively it. That's your equation. It's in point slope form. That's the equation of a line that kind of fits the data. It doesn't look as good this way. Usually we like to see it in slope-intercept form, which means solving for y. So I'm going to add 10 to both sides and see what you get. Again, I'll show you where this all comes from. That's fine. Distribute the 2. 2x minus 10 plus 10. Ooh, minus 10 plus 10, they cancel. That's it. Our line would be y equals 2x, which is cool. Let me tell you about point slope form really fast. Here's my aside. This is not just some weird magical equation. That comes from, watch this. If I were to think of x minus x1 as a quantity, which it is, you can divide both sides by anything in parentheses. You can move it by multiplication or division back and forth. So I'm going to divide both sides by x minus x1. And watch what happens. So that means if I divide the right by x minus x1, it cancels it. So it leaves me only m. And on the right, I just put it, literally divide by it. I'm going to put it underneath. See if this looks familiar. And then I just have m just cancels. Does that look familiar to you at all? This is my aside. This is the slope equation. So what's cool is that the slope equation, if you just manipulate it ever so slightly, that's where the point slope form comes from. So they're all interrelated. It's nothing from somebody's imagination. They just rearranged that a little bit and allowed you to find that missing point that would go in there to give you the appropriate slope that we already have. Okay, so that's where those come from. That's aside. We need to get rid of that aside because I need room. So I'm going to back up. I'm going to use my super cool eraser. Ready? Back to business. Let me tell you about the zero product property thingy. If I saw a graph like this, here it comes. Go purple. Go in purple. Whoosh. Let's do that. And I said it had roots of x equals a, x equals b, and x equals c. Like that. Those are places where the function would be equal to 0. And one of the things we can do for a function is that we can, get back to the red. If I say f of x, the one way I could represent this function with some minor details missing is this. X, this would represent those roots at least. Check this out. The only thing I would need to make this more accurate is I need one more point. If I were to find one more coordinate point on this graph, I could tell you what to multiply this by to get the proper amplitude. But as it is, right now, what I can say is that I do know in this particular function that for x minus a times x minus b times x minus c, if I set that equal to 0, I will get these particular roots that are shown in this graph. And I'm going to pull this aside. This is going to be a little bit of a confusion for some of you. When I set a function equal to 0, what that literally means is when is that graph at a height of 0? And if I look at this graph, I already know it's an x equals a, an x equals b, and x equals c. Another way to see where it's equal to 0 is if you can find out what value of x could I put in here to get 0 as a result when I'm done. In other words, how can I make this 0? Because if I could put a number in here, I took away a, and I got 0, 0 times anything would give me 0. If I could put a b in here, b minus b would be 0. 0 times whatever this stuff is, I don't care. I'd still get 0. Likewise with c. What we know is that to make this little 0, x were actually a, whatever a is a number, it could be 5, -2, whatever. If I put in a minus a would be 0. This whole function would be equal to 0. And that's a good thing, because that means I'm talking about a root. Anytime f of x equals 0, it's at a height of 0. It's called a root. So this 0 factor product property kind of quadratic formula piece that we'll get into, what we end up taking from this is, I know that this is equal to 0 if I can find what makes x minus a equal to 0. And I'm going to use a number example down below. I'm going to put actual values in there, and that helps some of you for sure. That means x equals a is one place where this function would be equal to 0, or be at a root, at a height of 0. Another one is, when is x minus b equal to 0? What would work there is, well, add b to both sides, and I get x equals b. That's another place that that function is equal to 0. And then last one, of course, when is x minus c equal to 0? Add x equals c, of course. So what we know is those are roots. Those are places where the function is equal to 0. Graphically, it looks like an x-intercept. Numerically on here, you just find places. You see what I did on the first one? That's an a. A on x minus a. Right? So that's a fun place to start. What if I did numbers? So try this. Given this little guy, if I said x minus 2, x plus 3, and x minus 5, if I set it equal to 0, I'm asking, where does this function have roots? Where does it hit that axis again and again? And the mechanical algebraic way we go about doing that is we take each little piece, x minus 2, set it equal to 0, and you probably already know it's just a matter of finding out what x makes that 0. And if you can do it mentally, do it. 2 is definitely what makes this 0. This one, -3 for the middle one, totally makes it 0. So I'm going to start just writing those in. There you go. And then the last one, of course, x equals 5 is the other one. Those are the places where that function would cross the x-axis. 2, -3, and 5. And that's really handy, because when we get to this thing called the old factoring stuff, one of the reasons we can factor, and one useful reason for factoring, is to get it into this form so we can quickly say, oh, it has roots at 2, -3, and 5, and you can move on. So it's a lot of stuff, but it's a good place to start. Okay, so we're trying to flip the page. It's 2-finger scroll on your marks. That's it. See that? That was awesome. Man, sometimes technology works. So the idea is we're solving the equations algebraically, and we just did this whole root thing. So if I could just factor number 5a and get it into that parenthesis times parenthesis, I could tell you what makes it 0. Okay, so I'm going to say, this is old school. If you have a quadratic with a leading coefficient of 1, take you back to your algebra days, you can factor by simply getting the factors of 4 that add to the middle term 5, and you're home free. As far as I know, x plus 4 and x plus 1 do it. And it's the same function, it's just written in factored form, which we love. Because if I say, when's it equal to 0, you're going, oh, I got it, Mr. C. All you have to do is find out what makes x plus 4 equal to 0. Got a little minus 4, minus 4. The other one is x plus 1 equals 0. Just minus 1. You get negative 1. Things are good. And then the next piece, I think that's it, right? We just stop there and say negative 4, negative 1. Those okay? I like them. But hopefully I got them. The next one is not in the same form. It has a common factor. This is another possibility. If you see a common factor that you can remove from each of those, I can divide out an x from each of those and get x squared minus 4. By dividing x out of each of those, remember you're dividing x out of each term, leaving behind x squared minus 4, and the x you divided out goes out front. It's factored. This little x by itself means that one of our possible roots, or one of our roots is x equals 0. You put 0 in for x, you're totally going to get 0. You guys have any cool ideas about x squared minus 4? What? Yeah, difference of perfect squares. So I'm going to put a little side note, and if it's cool, it's got to be in purple. So let's go. That's the same thing as the difference of perfect squares. Diff of perf squares. Now that is, talking about note-taking. I don't think I've written a full word yet on any of this stuff, so I apologize. So we're going to try x minus 4 times x plus 4. So x minus 2 times x plus 2. You find the square root of each of these, and you add up and subtract them. That means this whole thing actually factors to x times x minus 2 times x plus 2. We already know one of the roots is 0. The other would be 2 and negative 2 by looking at what makes those other parentheticals 0. So those are our roots. The last one, negative 4 and negative 1, 0, 2, and negative 1. We ran into something last block. I'm a little spacey coming out of break, and I goofed up. You notice the factors go in here for factored form, 4 and 1. Look at what the roots are compared to the factors. So when you do that kind of factoring, do you see what's going on? The roots versus the factors. Positive 4, then it turns to negative 4 and negative 1. Be careful. It's easy to mix those up. Like when you're doing factoring really fast, it is really easy to say the factors are 4 and 1, and you're like, oh, the roots are 4 and 1. But notice that the factors that you'd use to break up that quadratic are actually the opposite sign of what the actual roots end up being. So I'd say factors are opposite roots. Again, hey, there's 2 full words I wrote, factors and roots. They're illegible, they're full words. Yeah. Back in business. See, this is one of the pieces of, you got to get it equal to 0. That's one of our solving techniques when it comes to quadratics and other things. But we want to get them all on one side. So x squared, add 4x to both sides, subtract 8, so that you can have everything on the left. And you'll say, I'm going to do my darndest to try and find factors of negative 8 that add to 4. 8 and 1, 8, 2 and 4. No luck. They don't add to 4, so we have to go the other route, which brings us to our favorite. Yeah, the quadratic formula. I heard that whispered. It's only meant to be whispered. Negative b plus or minus the square root b squared minus 4ac. Rumor has it this was sung once, embarrassingly, at Prairie View. And then we got to find our a, b, and c. Remember, a goes with the coefficient of x squared. There's your b. And your c, keeping their signs. So x equals the opposite of b, plus or minus the square root of b squared minus 4ac, all over 2a. Does anyone know what I'm talking about? There, making progress. I put a, b, and c in their appropriate places.